All right, guys, we're going to go over this inference with means review. I'm going to break it up again, do first 10 and then the others. All right. So here on this first one, we are going to interpret the interval. Okay, so in actually interpreting the interval, not the confidence level. Okay, so remember, we're paying attention to what are we interpreting on here. So here were those number values when you actually made the interval. Okay, now let's talk about this because this wording is very tricky. So on this first one, it says there's a 95% chance that the true mean is in your interval. Okay, so that means it might be in your interval, it might not. Sometimes it is, sometimes it's not, especially when it says something like this, 95% of the time the true mean is in your interval. Okay, those are very similar in their meanings, and that's wrong. Those imply that the interval is stationary and the true mean moves around. Okay, so that is what makes the A, C, and then down here, same idea with this 95% probability. So intervals are not about the probabilities of items being in there. Okay, now here, so that leaves us with B and D. Let's see what we got. So we're 95% confident that the true average height of females at the school is the number that we got for our same sample result. Okay, so there's a problem. The true mean, we're not 95% confident the true mean is what I got in my sample. I'm 95% confident that the true mean is in my interval. Okay, I'm 95% confident that my interval was in the location to perhaps my interval contained the true mean. All right, number 2. Okay, so this one, after doing this problem, I think that this is a typo. It was also a problem that I didn't intend on putting type 2 error or p-value, and I noticed at the end there were some p-value questions. But anyway, so I think this is a typo because if you read here, it actually looks as though it's unsafe if they have at least 5 parts per billion. So that should actually be a greater than or equal to. And so we're going to start off saying that the oysters are okay unless we measure that they have 5 or more parts per billion of this type of chemical in them. Okay, so now remember that when we do this, when we talk errors, okay, you have to be clear on your HO and your HA. Okay, so with our HO, then, it stated it, okay, but what happens is the alternative is the one that is true. So that's, in this case, saying the oysters are unsafe, okay? But with a type 2 error, we fail to reject a false null hypothesis. Type 2 error, type 2 error. We failed to reject a false null hypothesis. So we think that HO is plausible. Also, the other meme, why reject the null? Okay? Why reject the null? You should have. Okay? So they are not safe, but I did not detect that they are unsafe. So let's go through here. First of all, you should be able to mark A off. A says they're safe, and we declare they are safe whenever they actually are. Okay, so there's actually no error happening there whatsoever. B says they are safe. The department says, yep, they're good, safe to eat, when in fact they are unsafe. Okay, so that is true. And so I was really liking that one a lot. And then I read answer C, and I'm like, okay, it says the same thing. They are safe to eat when in fact they are not. So first sentence on both B and C look good. So we'll analyze the second sentence in a minute. D real quick, let's see. The department cannot find evidence to say they are safe when in fact they are unsafe. They can, so, and then look at E. They cannot find evidence to declare them safe. Okay, so in both parts D and E, both of those statements are saying, you do or you do not have, whichever one it is, it doesn't matter, evidence of HO. We never ever say we have evidence or we do not have evidence of HO. Evidence is never about HO. The evidence that we get is always telling us if we have evidence or we do not have evidence to go with HA. Very important. So never say evidence regarding HO ever. So that's what makes both D and E bad. All right, so back to B and C. So the second sentence of B says, the public is put in jeopardy from eating the contaminated oysters. And that is true, that's what's happening. C says, fishermen get paid for their catch, and the public gets to eat oysters. Okay, that's also true. Okay, so both of those are true. But what's a consequence? In this regard, we're really thinking, okay, what's like a problem that is arising because of this error we are making? A bad thing isn't that the fishermen get to sell their catch and the public gets to eat them. Well, I mean, it kind of is. It's that the public is put in jeopardy because they're eating those oysters. Okay, so B was the better answer of those two consequences. All right, next. For which of these is appropriate to use a T procedure? So that's when we need sun. All right. So this actually threw me off at first. I was just looking for sun, and I went, oh, graph 1 is sun. Somewhat symmetric, unimodal, no outliers. Yep, we're good. That one is good. Picture 2 is not sun because it has outliers. Okay, so 2 is out. Picture 3 is skewed to the right. So my instinct went, oh, picture 3 is out. And then I went over here to the side because I thought 1 only was the answer, and there was no answer choice that said 1 only. So I went, ooh, I'm missing something. And that's when I noticed that the sample size for 3 is large enough. And remember that if it's large enough, I actually did not even have to draw out my data, because I know once all those samples fill in, it will be approximately normal, because of central limit theorem says that those sample sizes are large enough. So it will fill in to be approximately normal. All right. So therefore 1 and 3 are good. Okay. All right. 4 was doing an interval by hand. I've been kind of just going to the calculator whenever we've done a phantoms, or actually a panic when we've done an interval, okay? And I've even kind of started to do that on the 1 proportion and the 1 means, all right? But here's a issue, here's the type of problem where you have to know that formula. And so for that formula, we have to have that statistic, which in this case is the x bar, okay? So we have to have that x bar plus or minus your critical value, which is t star, and then you have to do your standard deviation or your standard error of that, and that's going to be your s of x over the square root of n. So here in this case, all of them say 5.4, so that's fine. I need to figure out what's the correct critical value. I can also figure out that I've got a few of these standard deviations or standard errors that are not correct. So I actually have a problem with the answer choices here, because I did inverse t of 1 tail, comma, 39 degrees of freedom. And I got 2.02. So none, answers D and E weren't right. I tried a whole bunch of other little things so I could maybe see what mistake the people who made these answer choices did, and I couldn't figure it out. So I don't know if it was a typo or what, but I think E is the one that they intended on being the answer. The 2.0, other than the 2.09 instead of 2.02, it was correct, had the correct standard error. All right, this one here, it asked for that critical value. So you need to find the critical value. While you may use the confidence level is what's in the middle. Use inverse T of one tail. Inverse T, if we have 98% in the middle, then we have 1% in the tails. And who's got a t-test? You must include the DF. So this was sample size of 15, 14 degrees of freedom. So then that was 2.624. All right, number 6. This was an interpretation of the interval. Okay, so I will be using this information with my interval numbers. Okay, so here we have again that 90% probability that the true one will be in the interval. That's saying the mean, true mean, moves around. So that's wrong. I think I did a typo here. It's probably supposed, it says 90%. Okay, yeah, so 90% of all of them are in my interval. 90% of all of that's again kind of like saying the true mean, or 90% of all of everybody's results are going to be in my interval. What if my interval happens to be a really funky outlier interval? Okay, so you can't say intervals are not about other people's results being in my interval. Mine could be funky and an outlier. All right, we're 90% confident that the average age, or the average student, drives between this much and this. Okay, I'm liking that one. That one's it. Let's look at the other one. Oh, if 50 random samples were done of 45 of them, how many? So 45 of those 50, that's about 90%. And what size interval? The 90 doesn't, and the resulting intervals. So we would do all of those resulting intervals. It didn't really say they were all 90% confidence intervals. But this one's saying how many of the resulting intervals will contain the true mean. So this one, part D, actually was the kind of more alluded to. I mean, I still see some problems with it, but it was more like a confidence level definition. Okay, and E, if we repeated this many, many times, I like it so far. If we had a whole bunch of intervals, then we would be getting my results 90% of the time. Okay, or that's saying the true mean. If we repeat it a whole bunch of times, the true mean is going to be in my interval 90% of the time. Again, that's implying the average real mean moves. All right, number 7. Here we have this interval and the claimed score. So that null hypothesis or claimed is 86. Well, what do you notice the connection between that interval and 86? And so the key thing that you're supposed to recognize is that 86 is not in that interval we made. Therefore, if I was to run a test, I probably would end up rejecting that null hypothesis. That's what I think. If I was to guess, that's what I think was going to happen when we run a test. I would find evidence to reject the null. The interval being completely contained below 86 probably going to give us evidence that the true mean is below 86. Okay? All right, now number 8 was running a full phantoms. So I tried to do that pretty clearly here. This was just about one mean. Now, interestingly enough, I went and I put it in my calculator. I did not do the calculating by hand. I did a one mean t test in the calculator. You can see I did not show the math work. And I'm fine with you guys doing that. More so because at this point in the game, I need you to understand the math and recognize, for example, the interval formulas and so on and so forth. But the issue arises when I just don't want you to make a careless mathematical error. So sometimes we can just go ahead and put it in our calculator to be more accurate, okay? This is the average length in seconds of all such advertisements I guess I should probably have put of 30-minute programs or all such 30-minute programs, okay? And they think it's longer, so our alternative is greater than. So this was a case where we had 21 randomly selected advertisements. Did we see that they were you know what, I didn't check to see if they stated that the population was approximately normally distributed. Okay, it didn't. I forgot when I did my key to look up there and say, does it say it's approximately normal? It doesn't say it. Therefore, I had to draw myself my dot plot. Okay? 21 is less than 10% of all such advertisements. 21 is not large enough. So look at how I labeled everything. These items were the number of seconds long for each advertisement, and I looked at the high and the low. The highest was 52. The lowest was 42. I subtract it and divide by 5, so I get about 5 bins, which I guess in this case I got 6 bins, but pretty close. Okay, so label, see all of my labeling, number of advertisements, and I did all my little tick marks, put everything in there. When I put everything in there, the data is sun, somewhat symmetric, unimodal, no outliers, therefore the approximately normal model applies. All right, and then again, I did it in my calculator. There was a very small p-value, so I rejected HO, and I have evidence that the average length in seconds of all such advertisements is greater than 45. So I have evidence of HA. All right, number 9 is a problem. I see that I did have random assignment, okay? That's always, when I see these words, randomly selected, random assignment, those are always triggers that I know I might have to reference later. So this was having middle school students, and they actually, I think, took 9 pairs of data. And so they had the paired data, and they did the average of their paired data. So they did the average of the sugar minus the sugar-free. So see, that null hypothesis would say on average there is little to no difference. Okay? They were wondering if the average of the sugar minus the sugar-free, I don't remember, they were just saying, is there an average difference in the reading times? Okay? So not equal to 0. All right, but I see this interval from negative 5.8 to positive 0.15. And that's interesting to me, because when I see that when I do sugar minus sugar free and I get a negative number to a positive number, 0 was in there. So I do not have evidence of a significant difference, okay? So that's what I'm looking for. I know that's going to be, concept-wise what they're looking for. So I see these ones talking about it includes 0. We don't have convincing evidence that the sugar causes faster reading times. Oh, maybe they wanted faster, so maybe this was a less than. Okay, but regardless, let's see, what are we doing? It has 0, so we do not have evidence of a difference. No evidence of a difference. Okay, C says we have evidence that sugar causes faster reading times. That's a no. The interval For C to be correct, the whole interval would be completely negative. Okay? All right. Now, A says because the confidence interval is the center of the interval is negative, then it's faster. D says because the confidence interval has more negative values than positive ones. Okay, so those don't matter. A and D are out. Now E made me think. E made me go, ooh, should I? Let's see. E says causation should not be inferred because the subjects were volunteers. And I remember there's something about that, we can't necessarily generalize if we have, okay, so being volunteers has to do with who we can generalize to. The thing that makes it an experiment for which we can do cause and effect has to do with it's an experiment. And we randomly assign to the treatment group so you can claim the cause and effect. See, so that is then what negates that one because we did have random assignment to the treatments. So yes, I could say cause and effect. Now, who I could generalize it to, that's another story. All right, this one was just wanting us to do a t-score. And the t-score value, x minus the mean over the standard deviation. Well, for t's, it's x bar minus true mean over the standard deviation of x bars, which this standard deviation of x bars is that x of x over the square root of n. Okay, and this is on your formula chart. So I just filled in the numbers. A was the answer. All right, so that takes us through those first 10 problems. I wanted to split this review in half because it gets really lengthy if I don't do that. So, done with that part.